Okay, so now we start the fourth video of this chapter 19. And what we are going to talk about now is resistors, but now they are in parallel. What does it mean? Well, here we have the battery creating this potential difference, VA minus VB. And then what we are going to do now is we are going to have different lines, and on each line we have a different resistor. So it's different from what we had before, where the resistors were in series and then all of them were in the same line. Here we have three different lines. In each one we have a different resistor. What does that mean? Well, let's summarize what we see from this drawing. Well, first thing is what we had already said. That's the kind of circuit that we have in our house, because if we turn off this device here, this one that has resistance R2, well, nothing will happen to R1 and R3. They will keep working. We don't break the circuit as we do in the case of the circuit in series. So this is very smart way of having the circuit, because we can turn off devices and the other ones will remain functioning. Okay, but what are the main points that we see here? First thing, just by looking at the drawing, you can see that all of the resistors are subjected to the same potential difference, right? Resistor 1, the one that has resistance 1, is under this potential difference VA minus VB. Same thing for the resistance 2, VA minus VB. Same thing for V3. So what we see now is that what is the same throughout the circuit, what is the same for all of the resistance when we have a circuit in parallel. Let's write this down. For the circuit in parallel, the potential difference, the VA minus VB, is the same for all the resistors, is the same for all resistors, right? So how is this different from the circuit in series? For the circuit in series, what was the same for all of the resistors was the current. The current didn't have another path to go, so it was the same for all of them. Here, no. For the resistors in parallel, what is the same for all of the resistance? The potential difference, this VA minus VB, which is the potential difference of our battery. All right. Now we come with the question, what happens now to the current? Well, as you see here, these resistors are drawing current from the battery to be able to work. But you see that the current is coming, but once it gets to this point, once it gets to this junction, it splits. So the current that goes through each one of these resistors do not have to be the same. It splits. So that's the other important observation. For a circuit in parallel, the current splits. The current that is drawn from the battery splits into currents I1, I2, I3. Each the current that goes through each one of these resistors. Okay, we could ask, what is this current? What is this total current that is draw from the battery? Again, similar to what we did for the resistors in series, we would immediately think about, well, let's try to use Ohm's law. The potential difference is equal to Ri. So I could try to get this I given this potential difference. But the question is, which R are we going to use here? So we want to think about a circuit that is equivalent to this circuit in parallel. That is, we want to think about a simplified circuit like this one, where I put a single resistance, but this single resistance is equivalent to the combination of all of these R1, R2, and R3. So this single resistance is what we call the equivalent resistance. So for the same battery, I have the same battery here and here, I have an equivalent resistance that will be drawn the same current that is drawn in this circuit. So I want to find out what is this equivalent resistance, because if I know what is this equivalent resistance, I come here to Ohm's law and I'll be able to find our current. Okay, so what I have to put in this equation for Ohm's law is this equivalent resistance. So what is it? Okay, so the way to go is, as this slide is showing, is to start from this equation. We all agreed already that the current splits, the current that is coming from the battery splits into I1, I2, and I3. So let's start from this equation. So let's write it again. I, the total current that is being drawn from the battery, which is also the total current that will be drawn by this equivalent circuit, by this equivalent resistance, is equal to I1, the current that goes through resistance 1, plus I2, resistance 2, plus I3. All right. But using Ohm's law, we know that I is equal to V over R. So let me use this into my equation. I is equal to V over R. Okay, so the total current that is being drawn from the battery is equal to V of the battery divided by resistance, which resistance? The equivalent resistance, right? If I would write this equation for this, let me come back. For this circuit here, I know that this current is the potential difference divided by this equivalent resistance. So that's what I wrote here. Okay, now let's come back to our original circuit. What is the current I1 that is going through this resistor that has resistance R1? Well, is this potential difference, VA minus VB, divided by this resistance. Well, what is this potential difference VA minus VB? Is again the potential difference of the battery, right? So this is again the potential difference of the battery. And we have here R1. And the same thing for I2. What is I2? The potential difference VA minus VB, which is the potential difference of the battery divided by R2. Okay, so V of the battery divided by R2. And what is I3? V of the battery divided by R3. Okay. With this, what do we conclude? Well, V is the same throughout. No? This is just the V of the battery. So we now get an equation which says that 1 over the equivalent resistance is equal to 1 over R1 plus 1 over R2 plus 1 over R3. This is the equation we were after. This is the equivalent resistance for a circuit that is in parallel. This is very important. Let's try to understand what this equation is telling us. Let's pick an example. Let me suppose, for example, that resistance 1, let's give some numbers. Let's suppose that resistance R1 was 10 ohms, resistance R2, let's imagine it was 20 ohms, and resistance R3, let's say, for example, 40 ohms. How do we get then the equivalent resistance for this example? Well, I have to put this in our equation, right? So I have 1 over 10 plus 1 over 20 plus 1 over 40. And how do we solve this? Well, we have to find the common denominator, which is 40. 40 divided by 10 gives us 4. 40 divided by 20 gives us 2. 40 divided by 40 is 1. Okay, so with this, we find that 1 over the equivalent resistance is 4 plus 2 is 6 plus 1 is 7, right? So we get 7 divided by 40. Well, how do we get this equivalent resistance now? We do a cross product, right? And we can say that the equivalent resistance is 40 divided by 7. What is this number? Well, I can check here in our calculator. So 40 divided by 7 give us 4.7 more or less. Okay, so conclusion, our equivalent resistance is 5.7 ohms. What do you see? That this equivalent resistance is smaller than any of those 3 resistance that we started from. So you see that the equivalent resistance in a circuit that is in parallel, now where the resistors are in parallel, decreases, is smaller than any of the resistances that we have in the circuit. Why is that? The resistance decreases because it becomes easier for the current to pass. If the current finds a resistance here that is too big, that is a big obstacle for it to flow, well, it avoids that one and goes through another one which is easier. So for the same potential difference in a circuit that is parallel, we'll be able to draw more current than in a circuit that is um, um, in a circuit that is in series. Now, it's easier for the current to flow. How can we try to understand why it gets easier for the current to flow when it has different paths to it? Let's make an analogy with water. Water here is flowing through these tubes because we have a potential difference, a gravitational potential difference. Here it's very high and here is much lower, so we have this water flowing. Imagine that we had just one tube. Well, we will have a certain amount of water flowing. But if we open another one, we'll have much more. The current will be much bigger because there are now two options. That's similar to what we have in this circuit where the resistors are in parallel. Once we add more path, more channels for the current, well, it will be easier for it to flow, so the total current will be larger. In other words, the resistance became smaller. It's again the same story as I say. Imagine if you had just one tube, but it was full of impurities blocking this current. No? So the water was like, we'll get drops coming out there. Well, if we put another tube that is very clean, whoo, we'll have a lot of water going on through the other one. So even though this was a big obstacle, well, we got to the water from the other tube. So that's the idea. The more channels we have, the more path we have for this current, the easier will be for it to flow. That, in other words, mean the equivalent resistance, now this equivalent resistance here will be small. Okay, so conclusion of all this story. When we have resistors in series, we add the resistances. So the resistance becomes much larger. Here in this slide, what we have is resistors in parallel. So how do we get to the equivalent resistance? By using this equation here, by using these ratios here, which means that the equivalent resistance becomes smaller. Okay, so I repeat. The equivalent resistance for a circuit where the resistors are in series is large, becomes larger than each individual resistance. The equivalent resistance of a circuit where the resistors are in parallel becomes smaller. It comes from this ratio, so it becomes smaller. We are now going to solve many problems where we are going to be playing with circuits which are either in parallel or in series or a combination of them. So we'll start now in the next lecture solving this problem.